Okay, welcome everyone. Today we have Daoji, who will tell us about standard monomials for Positroid varieties.
Thanks for the opportunity to speak at the seminar, and it's been almost a semester. I just want to say that I've learned a lot from you guys and very much appreciate it. Today I would like to tell you a story about standard monomials for Positroid varieties. Positroid varieties are a special class of subvarieties of Grassmannian, which kind of I see as a bridge between maybe the Mayflower world and the Schubert world. So I'm from a Schubert calculus perspective, so I will mostly tell the story from that, but there's not going to be much Schubert calculus in this talk. So it's going to be a talk mostly about the Hodge degeneration of the Grassmannian. So this is our friend, the Grassmannian, and the Plucker embedding, which we have seen many times this semester. And the Plucker embedding Grassmannians cut out by Plucker relations. And I would like to highlight a feature of the Plucker relation. So that's there at this poset for GR24, which is a poset on 2 element set on 4 elements. So the only non-comparable pair in this poset are 1, 4, and 2, 3. Right. So up to this the Plucker relation, if we model by the Plucker relation, every monomial in the coordinate ring of the Grassmannian can be written as a linear combination of monomials that are comparable. So because of that, for this particular example, we're all convinced that this works. Okay. And in general, so here I drew a larger poset for this is GR35. The Plucker ideal are generated by the Plucker relation, and the Plucker relation that I'm interested in look like this. So the feature of such Plucker relation is that for every non-comparable pair of indexing sets, Pi, Pj, I have a relation. The relation looks like the non-comparable pair followed by a linear combination of comparable pair with signs. Okay, so I would like to highlight that there are different versions of Plucker relations that you might see in the literature. In particular, this is not the version that you see on Wikipedia, for example. So just so that you get some more concrete idea. So here I have an example of this is a incomparable pair, and I can go through these columns and look at the first place where these things become incomparable. And this is sometimes called the multi-exchange relation. I find the first place where things incomparable, and I would take arbitrary permutation of the highlighted red numbers. And these are sometimes called straightening relations. And I can do this, I can do this, I get an expansion, and if in that expansion, if I still have terms that are incomparable, I can repeat that, and this place will become lower. So at the end, I will always be able to rewrite things so that every Lie term is followed by a bunch of incomparable Plucker pairs. Okay. So I would like you to take a mental picture of what this picture looks like. So Hodge in the 40s, using language that is not in terms of Gröbner geometry, and also I couldn't quite read this paper because it was written in the 40s, but essentially Hodge says that the degree D piece of the Plucker ring of the Grassmannian has a monomial basis that look like this. So it's a default product of the PIs, where all of the i's are comparable. Okay, So this forms the basis of the DEPs of the Grassmannian. In terms of Gröbner degeneration, we can think about Hodge's result as follows. So if we take a linear extension of the Plucker variable, so in particular, you can take the Lex order, that's a linear extension of the Plucker variable. And I would like my monomial order to be the Rev-Lex monomial order with respect to this linear extension on variable. So you might have seen the definition of Rev-Lex before, and maybe you don't remember the definition of Rev-Lex. So I would like to explain just a little bit how to think about Rev-Lex. So when you compare to monomial, that has the same degree. So each variable has a ranking. So you think about you have two sections of calculus. The two sections have the same number of students. Each student has a grade that corresponds to the ranking of the variable in the list. So we would like to compare which class did better. Okay, so if you want to do Lex, you go through top of the list. You compare your top student who does better. If you're doing Lex, the top student that does better wins. If the top student does the same, you go to the next student. Whoever does better wins. This is how you do Lex. How you do Rev-Lex is that you go through the bottom of you go through from bottom to top, and you look at who does less bad. So the worst student that does less bad wins. So this is Rev-Lex. You can just always, this is how I remember the definition of Rev-Lex. And the Rev-Lex is able to pick out, if you have a Plucker relation, if you think about the definition of Rev-Lex, always the incomparable pair. The incomparable pair would always win. Okay, but going back to the story, so here I will be able to give my definition of standard monomial, which is that if I have a subvariety in the Grassmannian, that I of x denoted its defining ideal in the Plucker embedding. A standard monomial for x is if it is not an element of the initial ideal.
Yeah. Could you say again why incomparable pairs always win? I didn't understand that.
Right, so let's look at a Plucker relation. 1, 4, 2, 3. Right, so if I have 1, 4, 2, 3, 1, 3 through 4, and 1, 2, 3, 4. Right, so you look at in each, let's say, why does 1, 4, and 2, 3 wins? Sorry, why does 1, 4 times 2, 3 win over 1, 3 times 2, 4? So so this is your two students in this pair, and this is your other two students in this pair.
Okay.
This student does worse than the student.
Thanks.
Right, and similarly, if it's the same thing. In particular, it's always going to win over the join times the meet. Okay, thanks for the question. Should have done an example. All right. Okay, so are we okay with definition of standard monomial? So, oh yeah, I would like to say that by general, of course, I define it for a subvariety of Grassmannian, but this definition is general for affine varieties and general Gröbner degeneration. And yeah, and sorry, let's just move on. So, so Hodge's results can be understood as follows. So because I explained how Rev-Lex works and how Plucker relations work, the initial ideal of the defining ideal of the Grassmannian is going to be generated by the monomials that are products of pairs of Plucker variables indexed by incomparable subsets. And the initial ideal of this monomial, under Stanley-Reisner correspondence, the simplicial complex is the order complex of the blue purple set or Young's lattice from the empty element to the top element. So the second bullet point follows directly from the first bullet point. And the standard monomials, meaning that the monomials that do not lie in the initial ideal, they are products of Plucker variables that can be totally ordered. So they can, in particular, they can repeat. And this, if I write it like this is a kind of object called a semistandard Young tableau. Let me remind you what that is. So it's a filling of boxes with numbers such that the numbers must increase in this direction, strictly increase in this direction and weakly increase in that direction. Okay, and that under the Rablex order that we have, the Plucker relation form a Gröbner basis.
Can you tell us one more time what are the Plucker relations?
Yeah,
This one.
Yeah, so you write down an incomparable pair. You can look for the first place where the two numbers are incomparable. And then that will define a red strip. And then you start to swap the depending on you swap things with signs, but you can take arbitrary permutation of numbers, take arbitrary permutation of the red numbers, and then and you remember the correct signs, and that will be a Plucker relation. So if you want to get rid of all the incomparable pairs, you can keep this process because does that make sense?
So when I take the permutation, like you're just asking which numbers do I move to the right and left? Like I switch 3 and 4, that doesn't count.
Yeah. 3, you remember the sign. Yeah, so you might get multiples, but that's okay.
Is it sufficient to just sum over like the shuffles?
Yeah, it's sufficient in this case. Yeah, it's sufficient to sum over the shuffles, but I want to say permutations because that's gonna later like what I generalize what our theorem looks like.
What is a shuffle?
Oh, you just this is a shuffle. like a card shuffle. Right, like
You're gonna fold some of the numbers on the left into the right and then twice.
yeah, because these are required to be ordered. These are required to be ordered. Yeah, a shuffle is a particular type of permutation.
So what's written there is a Plucker relation, or
there's
something else?
There's dots. I didn't list all of the terms. I don't do.
So all the terms except the first one are comparable?
Yeah. If you do this like shuffle once, this might not be able to get everything to be comparable. But this position where you encounter the incomparability will remove lower. So there's a process that can terminate.
So you do it again.
You can do it again, yes. So
the result of doing it again and again, that's what you call Plucker relation, or just doing it once is what you call Plucker relations?
The result of doing it, until the end, yeah.
That's a Plucker relation.
That's a, yeah.
You could also have multiple positions where it's incomparable there and leave this.
You could also have multiple rows where it's incomparable.
Yeah, but I mean, to write down a relation, all I'm saying is I have an algorithm I can follow. Yeah.
So in particular, each pi, pj for I and j incomparable, this appears exactly in one Plucker?
In this formula, yes.
Okay, great.
Yeah. So this is some of everything, these are all comparable. The lead term is not comparable.
So also those on the right are standards. So you can also say that Plucker relations are expressing the incomparable in the unique way in standard
Yes,
things.
yes. Yeah. Okay, so this is the basic story about degenerate the entire Grassmannian in the Fluker embedding under Hodge degeneration. Now let's degenerate subvarieties. Today my subvarieties will be Positroid varieties. Let me give you a brief overview of Positroid varieties. So the introduction of Positroid variety starts from the Hilbert stratification. The way I think about Hilbert stratification is that I can fix the reference flag. I can fix this to be the standard coordinate flag. And I compare the relative position between the K-plane with the standard flag. And the relative position, the possible relative positions are parameterized by the intersection of this K-plane with every step of the flag. And this data can be translated to the K-element subset of N-element sets. Are we all good with this? Okay. And one motivation for introducing Positroid variety was that at least this is written in the intro of the Knutson Lam Speyer paper, or that the Matroid decomposition, as many of the audience are experts on, they are complicated. So I put a sad face that they're complicated. So how do you get Matroid decomposition? Well, from the Hilbert's decomposition, I require fixed coordinate flag, the standard flag. To get a Matroid decomposition, I can take n factorial permutation of the coordinates. Each will give me a reference flag, a new reference flag, so I will get n factorial of them. They each induce the stratification. The GGMS intersects all of them together. Okay, so the middle ground, which defines the Positroid varieties, this is kind of in between. So instead of taking all n factorial different permutations of your standard flag, I take the cyclic permutations. So I take the cyclic intersections. Now instead of intersecting n factorial different stratifications, I intersect n of them. So it turns out that these Positroid varieties are much nicer. In particular, they're normal Macaulay with rational singularities. So let me, so this is, I guess I just, this is what I just said written in words. So to define Positroid variety, I take the standard flag, I define the jth rotation of the standard flag, and each rotation determines the Hilbert stratification and the Positroid stratification in this intersection. Okay. And this is what excuse me, the stratification looks like for Grassmannian 2-4. The picture is stolen from my academic older sister, Michelle Snyder's thesis. And so people have studied Positroid varieties. Like in particular in Michelle's thesis, I want to highlight that what Michelle does is that she puts these open charts around the torus fixed points on the Grassmannian. And she shows that each chart is stratified isomorphic to the Bruhat cell stratified by the opposite Bruhat variety in the affine type A flag variety. So this is the basic notion of Bruhat atlas. So this notion was later used by Thomas Lam, Stephen Karp, and Patrick Galashin in their study of regularity theorems of totally non-negative part of Gmod P's. So they use Michelle's idea. And let me just keep going. So let me give you an honest definition of how can I write down a Positroid variety. So the indexing, there are many different ways of writing down an indexing element for a Positroid variety because they're positroids. So one of the ways is by these objects called bounded affine permutations. So then affine permutation is a periodic permutation of the integers. The bounded affine permutations require an extra condition which says that the sum of fi minus I has to be k times n. So in terms of juggling patterns, this k in k Grassmannian means that you're juggling k balls. And bounded, this is the boundedness condition. So in particular, I can write down a bounded affine permutation by this window notation. So if I tell you where 1 to n go, I write down those numbers, I can expand this infinitely and periodically. Are you okay with this definition? Okay.
So the affine permutation is for some n.
You fix a gr kn. Yes. Yeah, so k is that k and is that n. And to get this bounded affine permutation from an element in Grassmannian, here's what you do. You write down its realization matrix, you extend this infinitely and periodically, and you define the where ith element go by this expression, right? So you take an I, you looked, if you're 0, then it's in the span of anything. So that gives you a loop. Otherwise, you look to the right, and you look for, let's say, you look for the first time that this vector appears in the span of the consecutive vectors from I plus 1 to j. So for example, f1 equals 4 because if I start here, it's not in the span of here, it's not in the span of these two, but it's in the span of these three, right? And then you'll because it's extended infinitely periodically, when you see f3 of 3 equals 7, you just keep going. Are we okay with this definition? Okay. So then the definition of positroid itself is that you collect the elements in the Grassmannian such that it gives you that bounded affine permutation. And the geometry of the Positroid varieties, the stratification is captured by the Bruhat order on the affine permutations, like that. Okay.
So you're saying for GR24, you have this picture with like 50 things on it. So they're like 50.
It's 33 for GR24.
That's a big number.
Yeah, so there are 33 bounded affine permutations, GR24. Yeah, so right, so connection with matroid literature and positroids. So maybe people are familiar, for people who are familiar with positroid cells, you literally replace the non-negative reals with C and take closure. That will get you the positroid variety. But by the way, most of these, I think maybe all of these things that will appear on the slides are due to Knutson Lam Speyer in their first positroid paper. And one really important feature for me today is going to be that they are irreducible varieties defined by cyclic rank conditions.
So closure is risky closure.
Yeah, closure is risky closure. Positroid varieties, from a Schubert perspective, they are the projections of Richardson varieties. So what are Richardson varieties are intersections of Schubert and opposite Schubert varieties in the big flag variety. And the projection is just you send it down the natural projection map. And if you insist that your top guy to be what's called a K-Grassmannian permutation, meaning that permutation that's allowed to have a single descent at position K, then there is a unique pair of U and B. And the dimension would be the difference in Bruhat length of U and B, if you insist that B is a K-Grassmannian permutation.
But there might be lots of, there's only certain pairs.
That's right, yes, right. No, but for any pair you project, you always get a Positroid variety. But just sometimes you don't get a birational map. Yeah, so for those that are birational, these are characterized by the top element being the Grassmannian.
So the affine permutations that you get, are those minimal length representatives somewhat?
They aren't in affine value.
Sure, but.
Yeah, so there's a way to, there's a combinatorial way that you can write down this F, and then you can spit out the UV. There's, maybe I didn't answer your question. Okay. Right, so because of this projection of Richardson's, the Positroid varieties are exactly the Frobenius split subvarieties under the standard splitting. So the standard splitting we get from standard splitting from the full flags. And our results heavily depend on the Frobenius splitness of the Positroid varieties. So because if I intersect, so because they're Frobenius split, they're all reduced, and if I intersect and decompose, I never run into non-reducedness. And this essentially, when we give our Gröbner basis result, this is essentially going to be the reason why we can concatenate the Gröbner base. I'll explain that in a little bit. So here is an example of the Positroid varieties. And so this is what I mean by cyclic rank conditions. So by cyclic rank conditions, I mean like these rank conditions can wrap around. But for example, you can't take that, you cannot take a V1 with V3 with V5 and impose a rank condition like that. That's not allowed. So as a projected Richardson variety, it's not, it shouldn't be obvious at all why you get this, but you do. I didn't write down the F for you, but it's okay.
So if you have a Richardson variety in the Grassmannian, it's one of these guys.
Yeah. Schuberts are special cases of Richardsons, are special cases of Positroid varieties. So in terms of these rank conditions, if you want to get a Schubert or opposite Schubert, you take the initial interval rank conditions. If you get Richardsons, you take rank conditions from the two ends. The Positroid, so there's a medium class which is interval Positroid varieties, which means that you're not allowed to wrap around, and those Positroid varieties have solved Schubert calculus, but in general, from a Schubert calculus perspective, Positroid varieties. But maybe let me not say that too much right now. But point is there are different kinds of Positroid varieties and with varying difficulties.
So I'm not sure if I understood. So every such cyclic rank condition gives me a Positroid variety. This is like
no, well, because if you impose arbitrary cyclic rank conditions, it might not be irreducible. But if you decompose,
then okay.
Yeah, it's still going to be cyclic rank conditions. So every Positroid varieties can be written as intersection of cyclic rank conditions. And in fact, if I only have one cyclic rank condition, I call that a basic Positroid variety. I can get the rest by intersecting the basic ones.
But also the other way around. If I put just the cyclic rank conditions, then every component is a Positroid variety.
Yeah, exactly. Yeah, that's because of Frobenius splitting. Yeah.
There's no other proof that it doesn't go through characteristic D, or that's your favorite proof.
For which fact?
That all these components that you get are Positroid varieties by intersecting cyclic conditions.
I don't know if you can. I don't know. Yeah. Thanks for the question. So, right. So now I'm ready to state our theorem. So I was only state our theorem for basic interval rank conditions, meaning that I have a single rank condition that does not wrap around. And in our paper, we say that, okay, if we understand this, we can get the rest by taking intersections of these conditions. And you have to be a bit careful if you have a wrapped around case. If you have a wrapped around interval, what you do is you go to the dual Grassmannian, it becomes a basic non-wrapped around interval, and you do things here, and we work through the technicality, and everything is fine. Just to go to the dual Grassmannian for the wrapped around case. But let me explain the just this simple case first. So if I have a basic rank condition in my example, so let's say if I take this Grassmannian, this basic rank condition, if I write down a semistandard tableau, which corresponds of k rows and d columns, d is the degree of my monomial. So if I take all of them, these are all of the standard monomial for the Grassmannian. For this particular interval Positroid variety, I ask for another condition, which is that it cannot contain a generalized anti-diagonal, which I define for you right now by this example. So my red numbers on the slides are generalized anti-diagonals. So they have to, the values of things on the generalized anti-diagonal have to sit inside this interval.
Typo, it should be anti-diagonal.
Anti-diagonal, I'm sorry, yeah, thank you, anti-diagonal. Because it runs from, yeah, so why is it anti-diagonal? Because it runs from northeast to southwest. So it needs to, it's a imposition is like weakly in columns and strictly in rows. So with tableau language, sometimes you can call this shape a vertical strip. Another way to think about this is that if you read this tableau in traditional Chinese or Japanese, you find an increasing subsequence that sits inside this interval of length rank +1. So because this is 2, 2 plus 1 is 3. So these generalized anti-diagonal have to be length 3. So if I am of this form, I am a standard monomial. Sorry, I am not a standard monomial. I live in the initial ideal if I contain a generalized anti-diagonal like this.
So in the third guy, could I have chosen 4, 5, and 6?
4, 5, and you could have. Yeah, it's not unique.
Also, it's weakly in rows and strictly in columns.
Then you mean in positions. You can have position, you can have repeated entries. No, you can take 2 entries from the same column, but you cannot take 2 entries in the same row. Yeah.
Sorry, and the length of the diagonal, that's 1 bigger than ranking.
Yeah, r plus 1. Yeah. Okay, so if you don't contain, if you are a semistandard tableau and you don't contain one of these, you are a standard monomial. Okay, so a Gröbner basis for this particular interval rank condition contains 2 classes of generators. So of course it will have to have the Kluger relations. So if if you take one of these, if you take a tableau that minimally contains a generalized anti-diagonal, meaning that you cannot delete 1 column and still contain 1. So for these minimal guys, what you do is you permute the numbers in the generalized anti-diagonal, and that will be your relation. And we prove that this is a Gröbner basis for this particular interval Positroid variety. And then we get this characterization by looking at really, so the Knutson Lam Speyer have a second paper on Positroid variety called Projections of Richardson Varieties. So there they describe the facets for the semi-Reisner complex in terms of chains in Bruja order. So we translate their condition, which is a very combinatorially non-trivial translation of their condition on Bruja order to conditions on Fluker's. So that this is how we got this this condition of containing a generalized anti-diagonal. Yeah, Trisha.
I didn't understand what you said about the deleting a column. If I delete the left-hand column and then choose 2, 3, 5, that still looks fine in the left line? Are you saying well, can you just repeat what you said again about deleting a column?
Oh, so I didn't, I guess, tell you, yeah, so I didn't write down the rank condition. So if this would be Grassmannian 3, 5, and the rank condition would be the rank of 2, 3, 4 is less than or equal to 2. So this is a Lie term because I cannot delete a column and still contain a generalized anti-diagonal. So you have to minimally contain a generalized anti-diagonal to be a Lie term. But otherwise, I don't.
So I don't have a generalized anti-diagonal with the numbers 2, 3, 4, you're saying?
Yes.
Okay.
Yeah, it has to be 2, 3, 4 because it has to live inside this interval. Yeah.
So the polynomial you wrote down as a degrees of polynomial?
Yeah.
In general, how big do your polynomials get?
You can take arbitrary permutations. So I guess the biggest it can be is number is the M factorial where M is the length of your generalized anti-diagonal. That's possible. Does that answer your question?
But like as a function of like K and N and A and B and R?
Well, the length of the generalized anti-diagonal is always R plus 1. So R plus 1 factorial, I guess.
But you asked for the degree or the number of monomials?
No, just the degree of the biggest generator that you can get in the Gröbner basis.
So that's without
Plus one.
factorial.
Huh?
That's without factorial.
So if you want the degree is like you have one entry in every column. That's the largest degree you can get.
So R plus 1.
R plus 1. Yeah.
And then in this process you just describe, so do you repeat it if there is another generalized anti-diagonal or?
Oh, you just take one. For each monomial, so for each Lie term, you can pick one and do this.
Because probably it will be like a Gröbner basis, but maybe not a reduced, I mean.
Yeah, right, yeah.
Right, so if, for example, if A is 2 and B is 5 and R equals 2,
Yeah,
the second monomial contains the generalized anti-diagonal, right?
yeah, that's
Like
fine.
2, 4, 5.
That's fine. Sorry, where? 2,
Second,
4,
yeah.
2, 4, 5. No, you can't have 5 because your interval condition is 2 to 4.
No, so if A is 2 and B is 5.
Oh, if A is 2, what's A? What's B?
The interval.
The interval.
Yes.
Yeah, so it's not a reduced Gröbner basis.
But she can do what she did for the Plucker relation, she can repeat.
Yeah, I can repeat. Yeah, I can repeat. If I repeat, I will get to repeat.
But is it a coincidence that these are all semi-standard?
Oh yeah, no, because the Plucker relation already took care of the non-semi-standardness.
But like if I change this, in the first one, if I change 135 to 134,
Yeah,
then when you do the swap, it's gonna no longer be.
I mean, I don't do the swap if I contain any non-comparableness because that's already taken care of by Plucker relation.
But also if that were 1, 3, 4, then you could delete a column and then you would have 2, 3, 4.
Yeah, I don't have to deal with non-comparable because Are you happy? Yeah, so how do you get it for all Positroid varieties? Well, you write down the ones for basic ones, you intersect, you can concatenate the Gröbner basis, and then you will get Gröbner basis for any Positroid variety.
So at the beginning, you chose like an ordering, like a linear extension of the Plucker poset.
Mhm.
Does that matter?
I don't think that matters. Yeah, like in nowhere in our proof depend on the particular linear extension. Okay. Let me talk about some applications. So what's this good for? So tableaux are a very important object in a big part of algebraic combinatorics. And here's an operation on tableau that's important for many different reasons, but let me tell you just an operation on tableau, and I'll relate that to standard monomials and Positroid varieties. So if I have a U-shape semi-standard Young tableau that looks like this, I can do a process called reverse stratification, which means that I take an outer corner, I will slide a number, an adjacent number to this dot into the dot, such in a way that I preserve the semi-standardness. So in particular, 3 cannot go here because 5 would be bigger than 3. So every step I have a unique choice. So this rule is described by this general schema. Okay. So just to perform some operations. So here, yeah, so 5 slides into the dot. I need to fill that dot. So 3 slides down, and this outer corner becomes the inner corner. There's nothing else to do. So this is the result. Okay. Equipped with definition of Jitaken, I can define promotion on rectangular shaped semi-standard Young tableau. This is defined on general shapes as well, but for rectangular shape, this is particularly interesting because as it turns out, promotion will give you a cyclic action on rectangular shaped semi-standard Young tableau, which is not true for general shapes. So let me define for you what promotion does. So I fix K, N, and D. So here my N is 5. So I can look for, right, so first of all, if 5 does not appear in my tableau anywhere, I just add 1 to everyone, and I'm done with my promotion. If 5 does appear, then I remove the 5. I do reverse stratification. These sides. And now the boxes will go to northwest. And replace the dots with 0 and add 1 to everyone. So this is the process of promotion on rectangular shaped semi-standard tableau, and should not be obvious at all why this is a cyclic action.
But you had some choices when you did this, like, or does it?
I don't have a choice.
Like in the second arrow, I could have slid the 4 down instead of the 4 to the.
You always want to attack a corner. That's not a corner.
Oh.
Yeah. Yeah. It's a completely deterministic process.
The order of the action is N.
Yeah, for rectangular shape, only for rectangular shape.
But N, what is N here? Is 5, you said?
N is the largest number that yeah. Sorry, N is the N in a Grassmannian essentially. Sorry, Anu?
What about for your top right box? This is symmetric about the diagonal. So why did you slide 4 down rather than 4 over? Is this a?
If I slide 4 over, I violate semi-standardness.
I see, thanks, yes.
Yeah.
So your rectangular shape may not know about N. Is that right? N is some label that you put inside.
Yeah, yeah. But I know that if my N does not appear, I add 1 to everyone. Yeah. So N dictates what the algorithm is. Yeah. Okay. All right. So why is this interesting? So Brandon Rhodes studies the what's called cyclicity phenomenon, which means that whenever you have a finite set equipped with a cyclic action, you can attach to that a polynomial, and if you evaluate this polynomial at n-through unity, it tells you, if I remember this correctly, the size of the fixed points under this action. So for semi-standard tableau, this is the relevant polynomial are called the Costin-Folkes polynomial, I believe. And these are the principal specialization of the short polynomials, up to a factor. And Gröbner proved this by using canonical basis, essentially, because they rotate nicely.
Is Costco foods?
Costco Fox, not Costa.
Costco.
Costco Fox, yes. Bad names. So promotion also shows up in web basis. So this combinatorial operation in the web basis literature, what's relevant is the promotion on standard tableau, and the web basis literature, they study spec modules, which are Europe's of Sn. So it's sort of a different story, but promotion shows up there. And it also shows up in geometric attaque, which Fontaine and Calmater recasted Rhodes' work of cyclic swimming phenomena in this GRT way, and gave some generalizations to other types. So we have natural cyclic rotation on the Grassmannian, which we can just shove the first vector to the end. So if I define this, I get a cyclic action on the Grassmannian. And Knutson Lam Speyer proved that if I have a Positroid variety, the rotation of the Positroid variety is again a Positroid variety. The Positroid variety behave well under cyclic rotations. Does anyone, so now I'm about to tell you a theorem. Does anyone want to guess what this theorem is?
Your basis behaves well under cyclic rotations.
Under
Monomials?
Yeah, in particular, yes. In particular, the cyclic rotation on monomials is promotion. Yeah. So our theorem says that promotion bijects the set of standard monomials of a Positroid variety with its cyclic shift. And you can really see that by our characterization of generalized anti-diagonal. So here, well, these are not standard monomials because these are in the initial ideal, but if I can show that the anti-diagonal rotate in a way that I expect, that this is true for the standard monomials as well. So here you can see that this is the result of promotion of that. This guy contains a generalized anti-diagonal for interval for this interval, and this is a cyclic rotation. So once you hit the boundary, once you wrap around, you have to go to the dual Grassmannian and work with intervals there. So the non-trivial power of theorem is that this process behaves well under taking the complement. So I'm not going to explain that in detail. Yes.
Is there a difference between the two cases of promotion? Like, do these behave differently when in promotion I have to like add the new thing or not?
I didn't understand your
So
question.
you said that in promotion there are just like two cases. The non-trivial one where you have an n and then you move these things around, and in the other case, what happens to these? The diagonal just stays.
Are you talking about how we deal with when the interval rank condition?
I'm just trying to understand the two cases of promotion in this context.
Oh, this is, sorry, yeah, okay, right. No, I understand what you're saying. So it's not one, I think it's, Bayron said two cases of promotion. There's only one promotion, which is promotion is purely defined combinatorially on tableau. That is promotion. This is just cyclic rotation of the Grassmannian. I wouldn't call this promotion. So yeah, so this is just, I rotate interval rank. So this is easy. And this is a promotion on the tableau. Yeah. Okay. Evacuation is another operation that shows up on tableau. And this is also shows up in representation theory. So in general, evacuation is difficult to define, but in our context, when you have a rectangular shape, this is what evacuation does. We just replace every entry with its complement and I rotate 180. And if you do that, you see that the anti-diagonal gets rotated. So this corresponds to, does anyone want to guess what geometry this corresponds to?
Duality.
What's duality?
Grassmannian is.
Oh, yeah, exactly. So I can swap these vectors. I do that. And that is induces involution in the Grassmannian, and this shows that evacuation behaves nicely under this duality. Yeah, so I have maybe 7 minutes. I'll talk briefly about our last application, which is we answer a question of Thomas Lam when he asked for a cyclic, a formula for what's called cyclic Demazure modules. I'll tell you in a bit what that means. So let me just give you a brief reminder what multigraded Hilbert series. So if I have a graded module whose grading satisfies, I didn't write the condition, but this grading needs to satisfy certain positivity condition. Let's ignore that for now. Just assume that its grading is nice. The Hilbert multigraded Hilbert polynomial is a generating function that remembers the dimension of each graded piece. Just a silly example to give you an idea. I take this module with this grading. I look at it with each degree. I look at their pieces. I get my generating functions, and this is my Hilbert series. Okay, and we can compute the Hilbert series of the Grassmannian and Positroid varieties under this particular grading, where I grade each Plucker variable by this indicator vector that indicates the k-element subset. So this is grading that comes from the small torus action on the Grassmannian under the Plucker embedding. And so for under this definition of multigraded Hilbert series, my multigraded Hilbert series for the entire Grassmannian is the sum over all of the semistandard tableaux of the right size with this weight. And similarly, I can restrict these to semistandard tableaux on that are standard monomers on the Positroid variety. Okay. And with this idea, we can get a recurrence on the Hilbert series of Positroid varieties. I don't have time to explain everything here, but the basic idea is that for every Positroid variety, you can intersect it with a hyperplane that's given by basically U. And you can exactly write down the components that show up in that. After you intersect with the hyperplane, these are exactly the varieties that show up. And the combinatorics we can write down. And the way we write this down is by relating the geometry of Positroid varieties to matrix Hilbert varieties, which Trisha talked about in her talk last week. And for matrix Hilbert varieties, we use the formula for Grothendieck polynomials, which are K polynomials for matrix Hilbert varieties. So we borrowed normal results from matrix Hilbert variety and the expansion of Grothendieck polynomials to get the summands here. So that's the basic idea. So now going back to the representation theory question that Thomas Lam asked, is that if I restrict the global section of a Bravais line bundle to a Positroid variety, well, in this case, the super variety, I get the what's called the Demazure modules, and these have formulas. It's called Demazure character formulas. And if I restrict to Positroid varieties, turns out the restriction is also surjective, and Thomas introduced these objects as cyclic Demazure modules, and he asked what a character formula is. So we can basically get this by taking the using our recursion from the Hilbert series and taking the correct degree part, and we got just the inductive formula for the cyclic Demazure characters. So it has a lot of signs, but the formula for Demazure character formula also has a lot of signs. So I guess what I want to say here is that, one last thing I would like to say is that you can also just get this character formula directly by using our condition that characterizes the standard monomials for Positroid varieties and some of the weights, and that will give you the same thing. Okay, I would like to just end my talk here. Thank you very much.
Questions?
Have you implemented these Gröbner bases in like Poly 2 or something similar?
We have not, but we should.
Your last theorem, is it equivalent to writing inequality in the K theory of the Grassmannian that expresses one positroid?
I think so. Yeah. Everything we do here in this paper is commutative algebra, but I think it can be done with geometry.
Any other questions? No, let's thank Daoji again.